imagine this. You're out in your garden, maybe, planting some flowers, perhaps digging a hole for a new fence post. Just a normal afternoon task. Then suddenly, your shovel just clangs against something hard, something heavy, metallic. It's definitely not a rock. It's not some lost coin. What if that thing buried right there was actually a silent witness, a key to unlocking millennia-old secrets about, global trade? It's pretty much exactly what kicked off this remarkable chain of discoveries in a quiet Swedish village back in 2022. Okay, so let's unpack this. Today we're diving deep into this really incredible story. It's about ancient metal, surprisingly complex trade routes, and how modern science is basically changing how we see connections across Europe way back in the Iron Age. Our mission for this deep dive, we want to explore how just one single find, seemingly isolated, how that combined with other discoveries and some really cutting-edge science can totally rewrite our understanding of historical networks.
Yeah, and what's so fascinating here, I think, is how these different pieces of evidence, one from a garden in Sweden, others from fields way over in Poland, how they can come together through science. They paint this really cohesive picture of an ancient world that was, much more connected than maybe we previously thought. We'll be digging into an interdisciplinary study published in the Journal of Archaeological Science, reports, and also looking at an article from the University of Gothenburg, just to see how these puzzles get solved piece by piece.
Okay, so let's go back to that garden find. It's autumn 2022, this village of Särdal, right on Sweden's west coast. A family's digging that fence post hole, and they hit this round, heavy metal object. But here's the kicker, the really interesting part. This wasn't just any old lump of metal. Nope. It was identified as the first complete plano-convex ingot ever documented in Sweden. Can you picture that? Sort of loaf-shaped, flat on one side, rounded on the other, perfect for stacking, for transport.
Standardized units, really.
And get this, the wildest part. This thing actually sat in their family workshop for nearly 50 years.
50 years?
Yeah.
Wow!
Can you imagine? Just sitting there, maybe a doorstop, who knows? Before an amateur historian, someone sharp-eyed spotted it and thought, hang on.
That's incredible. It really makes you wonder what else is out there just waiting.
Exactly. So this historian brings it to the attention of archaeologists.
Right. And these plano-convex ingots, they're pretty common finds, archaeologically speaking, across continental Europe, the Med, even up along the Atlantic coast. Their shape, their size, it varies a bit, but they were primarily used for transporting metal, both Bronze Age and Iron Age.
Okay.
So initially, looking at the Särdal ingot, its shape, size, weight, it definitely seemed like it could be Bronze Age. That was the first assumption.
Makes sense.
But,
Yeah.
and this is a big but, it was a single find, no archaeological context around it, nothing to help date it securely.
Right, just pulled out of the ground on its own.
Precisely. And that's where dating it became really challenging. You can't just guess. This is where the science becomes absolutely critical. We needed hard evidence.
So, okay, it's isolated, no context. How do you even start figuring out its age, let alone where it came from? This is where it gets really interesting, isn't it? They had to turn to forensic science, basically. Make the ingot talk.
That's a good way to put it.
They cleverly brought it into this bigger project they already had going, looking at Bronze Age metal trade. And they threw the book at it, scientifically speaking. Lead isotope analysis, elemental analysis, microanalysis.
Okay. The works. Exactly. And the results, they were a game changer. The elemental composition, which they measured using techniques like EDXRF and SEM-EDS, think of them as super precise scanners for figuring out exactly what atoms are in there.
Okay.
That analysis delivered the big surprise. The Särdal ingot was made of a quaternary copper-zinc-tin-lead alloy, so QSNZNPB, 4 metal.
Quaternary, meaning 4 components, copper, zinc, tin, lead.
Correct.
Right.
And that specific mix was a massive clue. It strongly suggested it was not Bronze Age.
Why not? What's different?
Well, during the Bronze Age, the main copper alloy was bronze, right? Copper and tin. Usually any zinc in there was accidental, very low levels, if any.
Okay.
The microstructure analysis backed this up too. It showed cast material, big grains, these little blobs of lead mixed in, but crucially, very low sulfur. That suggested it was smelted from a specific type of copper ore, oxidic ore, or maybe it had been really highly purified. Now, why this alloy is so significant, you need to understand a bit about the metallurgy. Bronze Age. Mostly copper tin. Zinc. Zinc smelts at a much lower temperature than copper.
Right.
So it tends to basically boil off, evaporate before the copper even gets properly melted. Making a deliberate copper-zinc alloy, like brass or this 4-part alloy, is tricky.
And more advanced techniques.
Exactly. Or specific ores where they occur together naturally in the right way. This quaternary alloy, with that noticeable zinc content, it became common much later in the Roman world for making brass. But finding it here suggests its presence way earlier in the pre-Roman Iron Age, which points to a big shift in metalworking know-how and the materials they had access to. It challenges what we thought they could do back then.
Wow, okay, so the alloy itself tells a story. But then it gets even crazier, right? This is where the collaboration comes in. The researchers in Sweden, looking at the results, the isotopes, the elements, they realized something. These results weren't just unique to their ingot, they were incredibly similar, like almost identical to artifacts found miles away.
Yeah, thousands of kilometers away, actually, in the Iława Lakeland region of northeastern Poland.
Poland, and how were those found?
Also quite interesting, found by a metal detectorist between 2013 and 2015, another case of accidental discovery driving the science.
Amazing. And what were these Polish finds?
They were a group of rod ingots found in 2 separate hoards, one with 2 rods, one with 6. And their shape, the manufacturing details, you could see casting seams, grinding marks, they strongly pointed to an early Iron Age date. We're talking maybe 650 down to about 250 BCE, roughly.
Okay, so similar time frame.
Yes. And some of these rods even had these sort of narrowed ends. It suggests they weren't just raw material, but maybe pre-made bits intended for making specific things, like ornaments, pectorals, neck rings, the kind of typical for the Pomeranian culture in that area.
So potentially part of a production chain.
Potentially, yes. It adds another layer. Then came the chemical analysis of these rods using ICP-MS, which is super sensitive for trace elements, and it confirmed it. They were chemically a very tight group, extremely similar to the Särdal ingot from Sweden, also that same QSNZMP alloy. Roughly 5% zinc, 3% lead, 5-7% tin.
That is astonishing. Sweden and Poland, same unusual alloy.
It really is, that similarity across that distance. That was the absolute key. It strongly suggested a shared origin for the metal itself.
Okay, so that's the next logical question. We've got Sweden, we've got Poland, same chemical fingerprint. Where did the copper originally come from? This is where lead isotope analysis comes in, right? You mentioned it earlier. How exactly does that work? What makes lead the key?
That's a great question. Lead isotope analysis is, it's a really well-established tool in archaeometallurgy. It works because lead has these unique properties. See, natural lead has 4 stable isotopes. Think of them as slightly different versions of the lead atom. And the ratio of these isotopes varies just a tiny bit depending on the geology, the age, and conditions when the ore deposit formed millions of years ago.
Okay, so different mines have different lead flavors.
Exactly. Each mine or mining region has a distinct isotopic signature, like a geological fingerprint. And the beauty is, this fingerprint doesn't change when the metal is smelted, melted down, mixed into an alloy, or remelted later. So we measure the lead isotope ratios in the artifact, the ingot, the rods, and compare them to this huge global database we have of signatures from known ore deposits. If you find a match, bingo. You've likely found the source.
Incredible detective work. So what did the tests show for the Swedish ingot and the Polish rods?
The results were, again, almost identical for both sets of artifacts, just remarkably consistent. And crucially, their lead isotope signatures matched up perfectly with the polymetallic mines down in southwestern Spain, specifically the region of Huelva and James.
Spain. All the way from Spain.
All the way from Spain. They mentioned specific mines like Aznalcollar and these banded ores from places called La Joya and San Telmo. And these Spanish mines, they have an incredibly long history. People were mining copper, lead, silver. They're way back in the Bronze Age, right through the Iron Age into the Roman period, a major mining center for millennia.
Okay.
So this analysis clearly established this shared, very distant origin for the metal in both the Swedish and Polish finds, a direct link. Southern Spain to northern Europe.
Right. Let's connect this to the bigger picture then. This is, honestly, it's mind-blowing. Before this, what did we generally think happened to those big Bronze Age trade routes, especially the ones bringing copper from Iberia northwards once iron started becoming common? Do we think they just faded away?
That was largely the assumption, yes. Or at least that the copper trade from Iberia might have become less important as iron took over for tools and weapons.
But this changes that narrative.
Fundamentally, these findings show that those trade routes established back in the late Bronze Age, the ones bringing Iberian copper up to Scandinavia, they didn't just vanish when the Iron Age dawned.
They adapted.
They adapted, they evolved, they continued. And significantly, it wasn't just raw copper anymore. It was these complex, ready-made alloys, like this quaternary one, being shipped across enormous distances.
That implies a really sophisticated system.
It really does. A vibrant, interconnected exchange network persisting well into the pre-Roman Iron Age. The fact you find artifacts with near-identical chemistry and isotopes in western Sweden and northeastern Poland, it strongly points to major maritime trade routes. Up the Atlantic coast, through the Kattegat, that strait between Denmark and Sweden, and then deep into the Baltic Sea area.
Does this fit with other evidence?
It does. It really corroborates earlier ideas about intense contacts between West Sweden and the Baltic region during this period. Ideas based on things like finding similar styles of house construction or shared burial rituals.
Okay.
But this adds a whole new layer. It shows the actual materials, the specific technologies, the alloys being moved. It suggests quite complex economic links, maybe even specialized production centers and distribution networks. It's more than just random trade.
So these aren't just lumps of metal. They're basically receipts for ancient globalization.
In a way, yes. Tangible proof of how surprisingly far-reaching and sophisticated these networks were. Connecting southern Spain to northern Europe long before we had modern maps or GPS or container ships.
It really speaks to their ingenuity, their drive for resources.
And their technological skill. Don't forget that. Making and trading these specific alloys shows real metallurgical understanding.
Yeah, absolutely. This whole deep dive, it just hammers home a point we keep coming back to on this show. These unique, isolated finds. The ones archaeologists sometimes find frustrating because they lack context. They can actually yield incredible, game-changing insights if you approach them with the right tools or right questions and that interdisciplinary mindset, bringing different kinds of science together.
Precisely. It's not just that science helps archaeology here. It's fundamentally redrawing the map of ancient connections. We're seeing evidence for what you could almost call pre-Roman manufacturing networks for specific advanced alloys. Not just shipping raw copper lumps.
That's a huge shift.
It is a huge shift in understanding the economic complexity and the technological level of the Iron Age. And this study, it's just a fantastic testament to combining that traditional archaeological work, careful recording of finds, understanding typology with these cutting-edge natural science methods. But just as importantly, it highlights the power of open science, collaboration, data sharing.
Right, because the Swedish team and the Polish team had to realize their results were so similar.
Exactly. If they hadn't shared their findings, hadn't realized the connection, and then decided to actively collaborate, these patterns, these continent-spanning links might have stayed hidden maybe for decades. Honestly, as someone working in archaeometallurgy, when you see a chemical and isotopic fingerprint match like this across that kind of distance, it really does send a shiver down your spine. It forces you to rethink interconnectedness.
Teamwork makes the dream work, even in archaeology.
It absolutely does. And it really makes you ask, doesn't it? How many other connections like this are just sitting there, waiting in the data from different projects, waiting for researchers to talk to each other and compare notes?
A really important point. So from a random lump of metal in a Swedish garden, one that sat ignored for half a century, to ancient mines deep in southern Spain, and then connecting all the way over to these rod ingots found by a detectorist in Poland, this deep dive has taken us on one heck of a journey across Iron Age Europe.
It really has.
It's a powerful reminder that trade back then wasn't just happening. It was robust. It was adaptive. It carried new technologies, new materials, new ideas across the continent. It shaped societies. What's the big takeaway for you looking back at this story?
For me, it's that demonstrated level of metallurgical sophistication combined with the sheer scale of the network. The quaternary alloy itself is significant, but seeing it turn up with the same source signature in Sweden and Poland, that speaks volumes about organization and long-distance exchange in the Iron Age. Much more dynamic than sometimes portrayed.
Yeah, for me, it's that resilience. The resilience of those trade routes, adapting from Bronze to Iron Age, and just the ingenuity of the people making it happen, moving not just stuff, but actual innovations in metalworking across distances we'd find challenging even today without modern tech. It's frankly astonishing. And this whole story just leaves you wondering, doesn't it? What other seemingly ordinary, isolated ancient objects are out there? Maybe sitting forgotten in a museum basement, maybe even still in someone's workshop like that ingot was, just waiting. Waiting for the right scientific analysis, the right collaboration to unlock their own incredible stories of ancient connections, ancient globalism. It's definitely something powerful for you to mull over until our next deep dive.